Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the transient behavior of RL network. So, in the previous lecture I have covered the transient behavior of RL series network using step input. I also covered transient behavior of RL series network using impulse input. Today I am going to discuss about the transient behavior of series RL circuit using sinusoidal input. So, circuit is given, suppose RL series circuit is given and input is your sinusoidal. This is your R, this is your IT. What is the behavior of the RL network when the input is sinusoidal? That I am going to discuss today. So, the series RL circuit is like this, simple, we can draw here. This is your R and this is your Vt. So, Vt is nothing but Vt is V sin omega t and this is the current IT. So, input voltage is Vt, which is V sin omega t. So, applying Kirchhoff's voltage law in this loop, so we can write the Vt is equal to RIT plus L dit upon dt. We can write. So, simple Kirchhoff's voltage law and Vt is equal to V sin omega t. So, we can write here. Now, this is a differential equation. So, to solve a differential equation either we go for the classical methods or a Laplace transform. So, here I am going to using the Laplace transform. So, take the Laplace transform on the both sides of this equation and this will come like this, RIS plus SLIS equal to V omega upon. So, Laplace transform, we know that Laplace transform of sin omega t is equal to omega upon s square plus omega square. Laplace transform of cos omega t is nothing but s upon s square upon omega square. So, taking Laplace transform on the both sides, and we know that the Laplace transform of this di upon dt, dit upon dt is SIS minus I0. So, here the initial condition is 0. So, here the initial condition is 0, that is why I0 is missing from this here, from here. So, RIS plus SLIS is equal to V omega upon S square plus omega square. Okay. Now, take the IS. So, we can take IS is equal to B omega L upon this we can get here. Okay. So, this is your constant. So, there are three roots. There are three can poles ka them poles they are at S is equal to minus R by L, and complex conjugate plus minus j omega, So there is one simple pole at minus R upon L, and one conjugate complex poles plus minus j omega. So what we will do, just to get the time behavior or time response of this, we take the inverse Laplace transform. From before going to take the inverse Laplace transform, what we will do, take the partial fraction expansion. So we carry out the partial fraction expansion. So this can be b omega L upon, this is outside, so this is 1, a1, a2 and a3. So a2 is nothing but it is complex conjugate. A2 is nothing but it is complex conjugate, or you can write, basically we can write, it is better to write A2 is equal to nothing but it is A1 conjugate. A2 is A1 conjugate. So this is the using the partial fraction expansion, we can just remove this one, this we can see, okay. Okay. So before carrying out the inverse Laplace transform, we carry out the partial fraction expansion, and we can find out the value of a1, a2 and a3. So where a1 is s minus j omega into this whole fs. So this and this cancel out and put s is equal to j omega. So we get this. So this is the a1, and a1 is, and a2 is a1 conjugate. So we straight away we can write, we can get here, this is twice j omega r minus j omega l. So this is the value of a2. This is the Heaviside expansion theorem, s plus j omega into 1 by s plus j omega whole terms, this one, this and this cancel out and put s is equal to minus j omega here. So we get this. So this way we can get the value of a1, a2, a3 we can get here s plus rl, s plus r by l, okay, into 1 upon s minus j omega into s plus j omega into s plus r by l, s is equal to minus r by l. So this first this and this cancel out, and now put here s is equal to minus r by l, and we can get this. So this is the value of a3, we can get, this is your a3. Okay, so we can get the value of a1, a2, a3 using the Heaviside expansion theorem. Now put the value of all the coefficients a1, a2, a3. Basically these are the pole residuals a1, a2, a3. So b omega upon L, this is the after putting a1, a2 and a3. So taking inverse Laplace transform. So b omega upon L, this is in time domain, b omega upon L. So L, this is your constant, So s minus this is basically, if you take the Laplace, suppose Is is equal to I1 is equal to K1 upon S minus j omega. So I1t will be K1 e to the power j omega t. Simple. So this similarly we can have this one is 1 minus j omega t for this, and e to the power minus r by L for this. So this is the inverse Laplace transform. Now we can rearrange just to get here I have taken this b upon twice j, this is outside, this and whole term 2 j omega outsides. Okay, so here this will cancel out, and this term is outside the bracket. So this is outside the bracket, this one, and b upon 2 j we have taken outside. So this is on simplification we get this. So now let r plus j omega L equal to j e to the power j theta. So basically it is in the rectangular form, and we are going to convert into the polar form. So say r plus j omega L is equal to j e to the power j theta, and r minus j omega L equal to z e to the power minus j theta. So what is the z? Z is the r square plus, so this is the magnitude, this is magnitude, and this is the phase angle, and theta is equal to tan inverse omega L upon r. So putting these values we get this, it is equal to v upon j, twice j e to the power j omega t e to the power j theta minus j omega t e to the power minus j theta. Now take this term in the numerator. So this will be j omega t. So basically I can write here e to the power j omega t upon e to the power j theta. So it can be written as e to the power j omega t minus theta. Similarly we can write for this term. So what is this? What is this? So this is the, we can express sine and cosine in terms of exponential. So basically this is the sine. So this is the it is equal to v upon z sine omega t minus theta plus v omega L upon z square e to the power minus r upon L into theta. So from the above equation it is clear that in series RL circuit current lags behind the voltage by an angle theta, which is given by tan inverse omega L upon r. If the resistance R is equal to 0, then theta is equal to 90 degree. So that is in the case of the perfect inductor. If the circuit is purely inductive, so current lags the voltage by 90 degree. Now come to the series RLC circuit. Series RLC circuit. So I have taken the transient behavior using the RL. First RL using step, impulse, now sinusoidal. Now I am going to discuss about the series RLC circuit using the, this is the step input. Step input. So this is series RL circuit. So apply Kirchhoff's voltage law. We can write this RIT plus L di upon dt plus 1 by C IT into dt integral over 0 to t is equal to VUT. So VUT is where if you remember ut is a unit step, its value is 1 for t greater than equal to 0 and 0 for t less than 0. Now take the Laplace transform, take Laplace transform on the both sides, take the Laplace transform on both sides, what we did in previous while discussing the RL circuit. So RIS again with initial current I0 is 0 and voltage across the capacitor or charge across the capacitor Q upon C and V0 is equal to 0. So setting initial condition 0, or we can say that the circuit is initially relaxed, there is no initial condition. So we can get the value of IS. This is the value of current I in S domain. We have to study the transient behavior, so we have to take the inverse of this to get the response in time domain. So before going to take inverse, first we discuss the what are the roots. So in this case this is the characteristic equation, this is equal to 0, so this is a second order system, degree is 2, so there are two roots S1 and S2. So let simplify omega is equal to some 1 by root LC and zeta omega 0 is R upon 2L and zeta is, so basically how it get it, basically for second order system, the general expression for a second order system is suppose any you can say the transfer function is omega n square s square plus twice zeta omega n s plus omega n square. So this is the general expression or transfer function of a second order system. So we can compare this with this previous one and we can get, so here say omega 0 is 1 by root LC and zeta omega 0 is R by 2L and zeta for the second order system zeta is R by 2, for series RL circuit zeta is R by 2 root over C by L. So just let omega 0 is 1 by root LC, zeta omega 0 R by 2L and zeta is R by 2 root over C by L. So then this S1 can be written as in terms of zeta and omega 0 and S2 is also can be written in terms of zeta and omega 0. So IS becomes this is the, now take the IT. So first before going to take IT inverse Laplace transform, what you have to do, you have to take the partial fraction expansion. So find the value of A and B. So this is the A is the pole residual of pole S1 and B is the pole residual of pole S2. So A we can get it, so this and this cancel out. So put S is equal to S1 here. So it is coming V by L S minus S1, S1 minus S2, and we can put the value of S1, this S1 and this S2 here and we get this. So this is the value of constant V upon twice omega 0 L root over zeta square upon L. Similarly, we can get the value of residual S B2. So, this and this cancel out and put S is equal to S2 in this expression, we can get this. So, this is your B, this is your B, which is coming twice omega 0 L root over zeta square minus 1. Now, putting this value of A and B, we get this is the expression for IS. So, this is the expression for IS in S domain. Now, take the inverse Laplace transform of this IS to just study the time behavior of this series RLC circuit when the input is a sinusoidal. So, this is your time domain response of a series RL circuit when it is excited by a step input, and after putting the value of S1 S2 we can get these expressions. So, V upon twice omega 0 L root over zeta square minus 1 e to power minus zeta omega 0 t. So, this is the final expression for current in time domain. So, depending upon this value R, L and C, there are 3 cases. So, zeta is, suppose zeta is greater than 1. So, this is the overdamped, and we know that zeta is equal to R by 2 root over C upon L. So, when the zeta is greater than 1, the behavior of the system is overdamped. When the zeta is less than 1, so this is the underdamped. And when zeta is 1, it is called critically damped. So, there are three cases depending upon the value of zeta, or zeta depends upon this circuit parameters R, L and C. So, this is the case for overdamped if R by 2L is greater than 1 by root LC. Basically, this is coming from this expression and this. Using this we can get this, and R by 2L is less than 1 by root LC, the case is underdamped, and when the R by 2L equal to the 1 by root LC, it is the critically damped. So, behavior is critically damped, and we can draw the graphical representation of these 3 cases. So, this is the underdamped, there is a peak overshoot and undershoot. So, this is the fast underdamped system is fast decaying, its transient will die out very fast, then critically damped and overdamped. So, these are the transient behavior of a series RLC circuit when it is excited by a step input. Similar behavior we can study if the input is your sinusoidal. So, in the next class we will discuss the transient behavior of series RL circuit when it is excited by a sinusoidal input. So, thank you very much. Jai Hind.